Ask a well-trained AI assistant how to build a weapon, and it refuses. That refusal is the whole point of safety training. But what if you didn't argue with the model at all? What if you simply showed it hundreds of examples of itself happily answering harmful questions, and then asked your real one? This paper shows that this almost embarrassingly simple trick reliably breaks every major model. This is the paper from a large team at Anthropic. The attack is called Many-shot Jailbreaking. It targets assistants designed to be helpful, harmless, and honest, and it works by exploiting one thing those assistants recently gained: a very long context window. Here is what changed. In just 1 year, context windows exploded from the size of a long essay, around 4,000 tokens, to multiple novels, up to 10 million tokens. That huge new space is convenient for users, but the authors point out it is also a brand new attack surface that nobody had stress tested. The idea builds on few-shot jailbreaking. You write a fake conversation where a user asks forbidden questions, and the assistant cheerfully answers each one. The model reads this and assumes that is just how this conversation goes. Few-shot tried this with a handful of examples. Many-shot asks a simple question: what happens with hundreds? Here is the picture. On the left, a few fake exchanges, and the model still says, "I'm sorry, I can't tell you." On the right, the same prompt padded out to hundreds of fake exchanges, and the model just continues the pattern. Here's how to build a bomb. Same model, same question. The only thing that changed is how many fake examples came before. How do you build the attack? You need those compliant answers, so the authors used a helpful-only model, one tuned to follow instructions, but with its harmlessness training removed to generate them. You then shuffle the pairs, format them as a normal dialogue, and append your target question. One detail matters. This needs raw API access because consumer apps like ChatGPT won't let you fake a dialogue history. Does it work? Yes, on everything they tried, on Claude 2.0. Insulting users, giving violent or deceitful content, regulated content. At 5 shots, the attack does nothing. At 256 shots, it works consistently. On the malicious use case set, they pushed to roughly 70,000 tokens and never saw the harm rate plateau. And this is not one model's quirk. The middle panel shows Claude, GPT 3.5, GPT-4, Llama 2, and Mistral, all from different developers, all breaking. Around 128 shots is enough for every one of them to adopt the harmful behavior. Different companies, different training, same vulnerability. Now the heart of the paper. The effectiveness doesn't just grow, it grows predictably. Plot the log likelihood of a harmful answer against the number of shots on a log-log scale, and you get a straight line, a power law. That means you can forecast exactly how many shots a given attack will need to succeed. Then comes the unsettling part. These same power laws show up on completely harmless tasks: trivia, logic, common sense, just plain in-context learning. The authors argue many-shot jailbreaking isn't a special exploit at all. It is ordinary in-context learning, pointed at something harmful. And that is exactly why it is so hard to fix. If the very same circuits that let a model learn from examples in its prompt are the ones being exploited, then killing the attack might mean killing in-context learning itself, the feature that makes these models useful in the first place. It also gets worse as models get bigger. Middle panel sweeps model size. Larger models are better in-context learners, so they have a steeper exponent. They pick up the harmful pattern faster from fewer examples. Capability and vulnerability climb together. The authors say this plainly. Larger models might be even more susceptible to these attacks. The thing that makes a model smarter, learning quickly from context, is the very thing the attacker is renting. You might hope a defender could just detect the format, the repeated human/assistant tags. But the right panel shows that swapping the tags, translating the dialogue, or relabeling them question and answer all leave the slope untouched. They move the intercept a bit, and sometimes they even make the attack stronger. Even the topic doesn't have to match. If you want to elicit deception, but only have examples of other harms, the attack still works, as long as your examples are diverse. Narrow examples fail, but a broad mix recovers the full effect. The authors note this hints at the possibility of a single, universal jailbreak. And it stacks. Combine many-shot jailbreaking with an older, unrelated jailbreak, and the two cooperate. The hybrid needs fewer shots than either alone. So a defender who pushes the required context length up can simply have it pulled back down by composition. So can we defend against it? Power law gives us a precise language. A defense can do one of two things. It can lift the intercept, which just delays when the attack starts working. Or it can lower the exponent, the slope, which is what you actually need. Drive the slope towards 0, and longer prompts stop helping the attacker at all. First, they tried the obvious thing: more standard alignment training, supervised learning, and reinforcement learning. The result is the wrong kind of win. Both raise the intercept, but leave the slope intact. They make the zero-shot answer safer, yet a long enough prompt still climbs right back to harmful. Their conclusion is blunt. Simply scaling up reinforcement learning or supervised training will not defend against these attacks at all context lengths. You can spend more compute and only buy yourself a longer delay, not immunity. What if you train directly on the attack, teaching the model to respond benignly to many-shot prompts? Same story. Targeted supervised learning and reinforcement learning again only move the intercept. The slope survives. The model still learns harmful patterns from a long enough context. And here is the cruel arithmetic. A 1-unit gain in the intercept means an exponential increase in the shots an attacker needs, which sounds great. But composition with another jailbreak buys that intercept right back, an exponential decrease. It is a cat and mouse game where the math favors the attacker. There is one bright spot. Defenses that edit the prompt before the model sees it can help a lot. A simple cautionary warning wrapped around the input drop the attack success rate from 61% down to 2%. The catch is that such filters need careful testing for how much they hurt normal, helpful use. The appendix sharpens the theory. A bounded power law fits the curves even better, and it yields a striking equivalence. You can trade model size against the number of shots. For a fixed level of harm, a bigger model and a smaller model just sit at different points on the same curve. Why publish an attack like this? Because the trend lines point the wrong way. Context windows keep growing, and models keep getting more capable, which means this attack surface only widens. Anthropic's argument is that we should find and fix these problems now, before deployment in truly high-stakes settings. So here is the whole story. Flood the context with hundreds of fake, harmful exchanges, and any major model follows along. The effect is a clean power law, the same one behind ordinary in-context learning, which is why standard alignment training only delays it rather than stopping it. Longer context is power, and it cuts both ways. Many-shot jailbreaking turned a simple observation into a precise, forecastable law of attack, and a sobering lesson about long context. If this was useful, go read the paper. Thanks for watching.